All right, guys, welcome to part two of our lesson in 1.1.1. Today, we're just going to be thinking and playing around with some um, polygons and assigning them to the correct spot. So, we're looking at a Venn diagram here, and one side has at least one pair of parallel sides, and the other side has at least two sides of equal length. Now, remember, parallel just means that if they were to go on forever, if two lines were to go on forever, they would never touch. So if we think about extending the sides, that means they would never touch. And equal length just means that both sides are the same size. So if we look at, let's look at this isosceles triangle right here, which means two sides are the same length. And I'm just going to look at each part of the Venn diagram and see if it fits in there or not. So does this isosceles triangle have at least one pair of parallel sides? No, it does not. So now this whole circle is ruled out, and I'm going to go over to this one. Let me come back. Don't let me. Don't let me. Okay. Does it have at least two sides of equal length? Yes, it does, right? We have the two top sides are equal length. Okay. Now, similarly, if we look at this square over here, and square, does the square have at least one pair of parallel sides? Yes, it does. So we know it belongs in this green circle. And now we're going to go over, does it have at least two sides of equal length? Yes, it does. Squares have the same side of equal length all around. So that belongs in both circles or in the middle. And we can just keep doing this. So here we have a parallelogram. At least one pair of parallel sides? Yes. And two sides of an equal length? Yes. Basically a slanted square. This one is parallelogram, could be like a slanted rectangle. Either way, it's going to have two pairs of equal side length. Here is another parallelogram, same thing. Or the first one was a rhombus, but it's the same idea. That's the slanted square. And parallelogram, same idea. It has both parallel sides and two sides of at least equal length. Isosceles trapezoid, same thing, right? We have the top and the bottom are parallel lines, and they have the two sides are equal length, so that also belongs in the middle here. Equilateral triangle. It doesn't have any parallel sides, but it does have sides of equal length, so we're going to slap it there. Let's go to this regular hexagon. It does have parallel sides. If you look on the opposite side, it's parallel, and they all have equal length, so that belongs in both. The pentagon. So for this regular pentagon, this pentagon does not have parallel sides, but they are all of equal length. Rectangle, much like the square, has parallel sides and sides that are the same length. This triangle looks scalene, so it doesn't look like it has any parallel sides or two things that are equal length, so we leave this outside the diagram. Same with this triangle. This is another scalene triangle. This one just looks obtuse. Same thing, no parallel sides, no sides of the same length, so we're going to leave that one outside. This isosceles triangle has, is that isosceles? Yes. Isosceles triangle, that has two sides of equal length, but no parallel sides. This trapezoid has parallel sides, but no side of equal length, right? It looks like the two side ones are messed up. This quadrilateral looks, that's actually like a kite. So a kite actually has two equal sides. So we're going to put it there, but it doesn't have anything parallel. And then this other thing also has, this other trapezoid has two pairs of parallel sides, or one pair of parallel sides, two sides are parallel, but no sides are the same length. And then our last one here, I might have to move me real quick. Let's move me over the side just a little bit. And then it looks like we have another kite. That kite, again, has no parallel sides, but it does have ones of equal length. And that's going to be it for this one. And so now we're going to move over and check this one out and do the same thing again. And again, I'm going to check one thing at a time and see if it belongs in one or both. Isosceles triangle has only three sides. That is true. It does not have a right angle, so we're going to leave it there. Square obviously has more than three sides, but it does have a right angle, so we're going to put it in there. We have a rhombus. The rhombus has more and does not have a right angle because it's slanted, so we leave that one outside. Parallelogram, more than three sides, no right angles, so this one gets left outside as well. Trapezoid, same thing. Automatically has more than three sides, no right angle. Equilateral triangle has only three sides, has a right angle. This triangle has three sides and a right angle, so we're going to go in the middle. Pentagon, neither of them goes out. This this kite has neither, so we leave that out. This has a right angle, but more than three sides. This has neither of those, so we leave it out. Our rectangle here has right angles. Our hexagon has none of them, and this triangle has three sides, but does not appear to have a right angle. And then I'm just going to make sure I'm not missing one by moving me. I don't think I am. Oh, I'm missing two. It's a good thing I'm moving myself. Okay. So, isosceles triangle here. This one has a right angle and has three sides, so we're going to put it on both. And then again, we have another kite, no right angle, and has more than three sides, so that one's out. I'm going to move myself back. We got one more to go through, and this one is more what this section is about. So, it has reflection symmetry and has 180 degrees rotation symmetry. Our isosceles triangle has reflection symmetry down the middle, but if we rotate it 180 degrees, it's going to be upside down, hanging the wrong way. So that's a no-go. The square has reflection symmetry 4 ways, and you can also rotate it 180 degrees and get it itself. If we flip it upside down right, it's going to be itself. The rhombus has both. We can slice it down vertically or horizontally, and that's our reflection symmetry. And then if we flip it up, or if we rotate it 180 degrees, flip it around, it looks like itself. The parallelogram does not have reflection symmetry because if we were to draw a line across like that, that obviously wouldn't work. And then even if we slant our line like that, one point is going to look higher than the other. So we do not have reflectional symmetry there. And if we rotate it 180 degrees, we have to think about this. If we rotate this 180 degrees, will it look the same? So I like to pick a point, and I like to see if that point would end up where I want it to. So if I'm looking strictly right there, and I rotate this 180 degrees, is that going to end up there? Yes, it will. And will this point here end up here instead of somewhere else weird? Yes, it will. So it does have reflection symmetry, or rotation symmetry, sorry, 180-degree rotation symmetry. So we're going to put it there. This has reflection symmetry, but it doesn't have rotation symmetry. Again, if it flips it upside down, it is, or if we rotate it, I shouldn't say flip, if we rotate it upside down, triangle is going to be pointing down. This has reflection symmetry, but it does not have rotation symmetry. The top and bottom sides have different lengths, so that won't be the same. This doesn't have reflection symmetry or rotation symmetry, so we're going to leave that one out. This, likewise, has no reflection symmetry and no 180-degree rotation symmetry. This has reflection symmetry, but does this have 180-degree rotation symmetry? So let's think about this for a second. 180-degree rotation means rotate it upside down. So it does not, because it will be pointing upside down. So just has reflection symmetry. Hexagon has both, right? You can slice it down vertically. Basically, the two endpoints or vertexes anywhere, vertices. You can slice down the opposite ones, and you can have reflection symmetry that way. And if we rotated it upside down 180 degrees, it would look like itself. Here we have reflection symmetry with the kites. I might as well get both the kites while we're at it, because they will act the same. So both the kites are going to act the same. They both have reflection symmetry, but if you turn them 180 degrees, if you rotate them upside down, they're not going to look the same. This trapezoid has neither. It doesn't look the same. If you rotate 180 degrees, it's going to be pointing down, and there's no line where we can draw there to have it reflect on itself. This rectangle is going to be both. I think that one's somewhat self-explanatory. You have the reflections vertically and horizontally, and then if you turn it upside down, rotate it upside down, it becomes itself. Triangle. This sailing triangle has neither, and this triangle also has reflection symmetry, but not 180 degree rotation symmetry. Because if we turn it 180 degrees, it is going to look like that. So that is all for part 2. Hopefully this just gets you thinking about polygons and being able to categorize them and their appropriate spots. And this wraps up 1.1.1.